Okay, hello everybody. Thank you very much for the invitation. So, Young Song Wang is my PhD student and he is still working on his document. So I prefer he still work on his document because his defense will be by the end of this year. So I come to make the speech. So the idea is to talk about some topics about efficient Monte Carlo Neutron transport calculation on advanced architecture and especially on many core architectures. And I will focus especially on a specific point of Monte Carlo Neutron transport. Some words about Monte Carlo particle transport and especially the cross-section management in Monte Carlo calculation. Just a few slides about the PATMOS prototype, which is actually the code we develop in order to test all these features about our architectures, both in terms of software architectures and computer architectures. And the solution we implement concerning the management of the cross-section, and two different approaches. One is classical one, which is the energy lookups algorithms, and another one which is quite new, and this is the multiple representation of the cross-section, and some perspective and conclusion. Okay, so Monte Carlo neutron transport. So the main principle of Monte Carlo transport for neutrons. The idea is to follow each particle from birth to absorption or leakage, so to the depth of the particle. And all the trajectories of the particle are governed by interaction probabilities described by microscopic cross-section. So we can have a particle which have no collision. In this case, she cross a material and she has no interaction with any other particles. You can have some interaction and an absorption of the particle. She disappears, and other one she can have some different interaction with all the particles and have a strange trajectories, what we call the diffusion. So all these cases depends on essentially on the energy, and all the probabilities of these different interactions are represented by the cross-section. So the cross-section is the probability of interaction with another particles depending on the energy. If we consider what are the main advantages of using this kind of approach to simulate and to solve the neutron transport equation, so the main advantage is that it's very precise simulation, numerically accurate with minimal approximation, because we compute all the interaction of all the particles. It's embarrassingly parallel workload, since all the particles are quite independent from each other, and individual histories of each particle are totally independent. But the main challenge is very time consuming, because we have to simulate many different particles in order to have a convergence of the system. And if we consider modern architectures, we have some main drawback of this kind of simulation, because we have to adapt to the computing accelerators of modern architectures. With multi-level parallelisms, we have a little natural vectorization potential of this kind of algorithms, and also a large memory requirements. So the main hotspot of this kind of calculation is the cross-section management. So just to show you, just for some isotopes, the number of data we have to store inside the memory in order to have all the information necessary to compute all the different interaction depending on the energy. So many different data to store and to manage. And when we achieve a simulation using this kind of approach, up to 80% of overall computing time is due to going inside memory and try to find the right cross-section at the right energy depending on the particle we are looking at. So the main algorithm which is used at the present time, the classical one, is a classical binary search inside a large table stored in the memory. And so many people are looking at how to deal with this problem, especially when we are looking at many core architectures or even GPU architectures and so on, and how to deal with this kind of bottleneck of accessing memory and quite randomly inside a large table inside the memory. So when you make some analysis, some performance analysis, you see that the energy grid is accessed randomly. The floating point unit is mostly idle because of cache misses, because we are going at each time to try to look at the memory to find the right value. And if we have some vector units, the vector units are doing nothing. So this is the best case in order to make some optimization. And so what the idea of the job is to focus on this point and try to optimize the cross-section lookups algorithms, both in terms of CPU performances and memory footprint, because we can have some variation of this kind of algorithms, but we can also increase the memory in order to increase the performances. So we don't want to have too much increase of memory footprint. We focus mainly on many core architectures in order to exploit multi-level parallelisms and vectorization, and to try to find efficient approaches for many core architectures. And we will see that we try to go from a memory-bound problem to a CPU-bound problem. So we study mainly two different approaches. So the classical one, where the cross-sections are pre-computed and stored inside memory, and try to find an optimal energy lookup algorithms with the best compromise and best balance between performances and memory footprint. And another one where we do not store, or we store minimal information inside memory and we compute on the fly all the cross-section. Some words about the PATMOS prototype. So initially, the reference code we developed at CA is the Tripoli code. This is a development from the 90s, and we have now some issues with new hardware. So all the code is in C++, is a parallel version of the code. The code is parallel using MPI, but only one level of parallelism, only MPI, flat MPI parallelism. And the number of lines is quite large, so it's quite difficult to make some experimentation on this code if we want to modify the software architecture and so on. So the idea is to develop a new architecture, a new code called PATMOS for Particle Transport Monte Carlo Object-Oriented System. And the idea is to focus first on the software architecture and to adapt the software architecture to new computing architecture, and to add, after that, all the physics we need in order to make some realistic simulation. And so this is first a lightweight prototype developed in C++. And so, as I said before, simplified neutron physics, but complex enough to represent all real Monte Carlo code. And when we have the software architecture we want, we will add all the physics we want. So some words about the experimental environment we tested. So concerning hardware, we test both classical Xeon architecture with Sandy Bridge and Broadwell, and also two versions of the Xeon Phi architecture with the KNC and the KNL. And we use a simple test case, a classical one in Monte Carlo Transport called point kernel. So first, about some optimization about the energy lookups algorithms. So the first, does it work? Yes. The first is the classical one, which is implemented in most of the transport, Monte Carlo transport code, the binary search. And we study and implement different versions of this research in the table, the cascading isotope hash material, SCMD, and unionized. And this is some variation of the classical one, and try to see the performances we can obtain, the effort we can do on vectorization, and depending on the algorithms, we have some potential of multi-level parallelism and vectorization of this kind of algorithms, and also the memory footprint. So the reference is always the binary search, and we have some speed up depending on the version of the algorithm we use. So on CPU, on classical CPU, I think on this experiment it was not Broadwell, it was the Sandy Bridge processor, and we obtained up to a factor 3 acceleration with the unionized, but you see that the memory footprint is huge, since we have up to almost 6 gigabyte compared to 500 megabyte. And on the mic, so this is the KNC version of the mic with 60 threads or 240 threads. We obtain some interesting speed up too. But also a great increase of memory. And also we have, in this first version of implementation, we have some problems of optimization in terms of memory, since we should have exactly the same memory footprint on the CPU version and on the mic version. And that's not the case. So we make some optimization, and especially on memory optimization and the way we deal with the data in the memory, in order to obtain exactly the same memory footprint depending on the architecture. And we obtain also some interesting speed up with this version. So we can find some different version of algorithms, and we can have some optimization, and we can find the best balance between performances and memory footprint depending on the architecture. And as you can see, the CPU is still the best compared to the KNC, but with a quite similar time for the binary search, for example. So this is the first step of the work, and now we try to think differently and to say, okay. We test many different kind of algorithms, and we see that we can make some optimization, but we still have a large amount of memory to store, and we cannot have some great acceleration. So the idea is to think differently and to propose a new way to deal with this cross section. And we look at the multipole method, where all the cross-sections are computed on the fly and not stored in memory, are not pre-computed. The main advantage of this method is we drastically decrease the memory footprint, and so we can imagine some calculation that we cannot achieve using the first approaches. Essentially, where the temperature, if you look at some physical test cases where the large variation of temperature, you need to store a very large amount of data in the memory, because the cross-section vary depending on the energy, but also depending on the temperature. So if we use classical approaches, we cannot make this kind of simulation. With this kind of approach, we can realize this kind of simulation. So we have no more lookup on the memory, no more memory bound. There is also high SCMD potential, so what's quite ideal for mic architecture. and we go from several gigabytes of memory to a dozen of megabytes. So we start with these algorithms, which was a quite naive algorithms with some potential of optimization, because the computing time using a binary search compared to this kind of approach, the decrease of performance is about 1 or 2 orders of magnitude. So, okay, it's interesting to have to minimize the memory footprint, but not to have this kind of decreasing of performances between the two approaches. So we made some optimization efforts. So we start to try to simplify the algorithms. We remove the duplicates, strength reduction, and so on and so on. We work quite hard on vectorization. We move the branching inside a loop. So classical optimization when you are looking at an algorithms. Loop splitting. We test also the double to float representation and try to see if we can have some acceleration due to this kind of optimization, and of course look at the precision, the precision of the results, not decreasing the precision of the results. Classical also optimization about the way we store the data from a structure of array to or array of structure to structure of array. We focus on the element in memory, data padding, and scaling. And we test this on both on Broadwell and KNL. And so we have the blue bar is about Broadwell performances, and the red bar are for the KNL performances in gigaflops. And we test each optimization. So when we put simplified algo, when we put SCMD, is simplified algo plus SCMD optimization. So we add all the optimization. And finally, we can obtain some very interesting performances, and we obtain very interesting performances on the KNL up to this number, which is 1.8 teraflops. I think it was using all the threads. So it's very interesting, but on this slide, I don't put exactly the comparison between the classical approach we using binary search with this multiple representation, because we have to find the good test case and the good benchmark to compare exactly the two approaches. But of course, even we did some optimization and we obtained some very interesting acceleration. The multiple representation approach is still slower than the binary search approach, but it can allow some simulation what we cannot achieve using the binary search or classical lookup algorithms approaches. In terms of conclusion, so we study and implement various energy lookups algorithms to find the best balance between the performances and the memory footprint. We implement the multiple approach, which have a high SCMD potential, and we go from a memory bound problem to a CPU bound and to a compute bound problem, which is quite interesting. And we obtain up to 1.8 teraflops in single precision. So as I said before, since the memory footprint is very low, it allows new kinds of simulation which were impossible with classical approaches. And concerning the future work, we had some optimization and variation about the multiple approach. In order to optimize this way of computing and manage the cross-section. Try to also to test the other KNL features. We don't test the different way to use the KNL and the different use of the memory, MCD RAM, flat, and so on and so on. We still have in mind to look at the GPU, but at the present time we don't have made some tests on this kind of architecture. So the next work we want to achieve is to use the PCP machines and to take into account the energy consumption. And because we look at the CPU performances, we look at the memory footprint, what could be interesting is also to look at the memory the energy consumption, and to see if we increase the CPU consumption, if we decrease the memory footprint, what about the energy consumption of this kind of approach, and to compare, to have another element of comparison between the two approaches. Okay, thank you.